everyone, and welcome to Talk Nerdy. Today is Monday, September 9th, 2019, and I'm the host of the show, Cara Santa Maria. Now, first and foremost, I want to thank all of you who made Talk Nerdy possible this week by pledging your support at patreon.com/talknerdy. Our top supporters include Dudus Infinitus, Phil T-Bear, The Zombie Drummer, David J.E. Smith, Brian Holden, and Jeffrey Sewell. If you want to hear your name at the top of the show, just got to go to www.patreon.com/talknerdy and pledge your support. Remember, Talk Nerdy is and will always be 100% free to download, and that's because of listener support from people just like you. There's other ways to pledge your support, though. You don't have to spend any money at all. You can just rate and review on Google Podcasts or Apple Podcasts or anywhere you get your podcast, maybe Spotify, maybe Pandora. I think I'm in all those places. Yeah, but you know what? Enough about that. Let's dive into the show. Super exciting episode this week, and the first time that I got to do an in-studio recording in quite some time. Actually in my brand new studio, so it was a bit messy. But she put up with me, Dr. Sabrina Stierwalt. She's an extragalactic astrophysicist, and she's interested in the formation and evolution of galaxies. Now, she is just started a new job at Occidental. So she was just down the street from me before we did our recording, which was very exciting. And I know you're going to love this chat just as much as I did. So without any further ado, here she is, Dr. Sabrina Stierwalt. Well, Sabrina, thank you so much for joining me today.
Thanks for having me.
Of course. I'm really excited to be talking nerdy with you in the first ever recording in my brand new studio in my brand new house.
Ooh, I feel very special.
And I'm really, really close to where did you say you're just starting at Occidental?
Yes, this was my second day.
Oh my gosh, I'm so lucky. You must be exhausted and a little overwhelmed.
I've been all day orientation.
Oh, wow. Oh, so you're still in. Okay, so
yes.
Does school start next week?
Yes.
Yeah, gotcha.
Yeah.
And you are, what's your title there?
Professor of Physics.
Professor of Physics. And are you going to be teaching this semester?
Yes,
What
I'm
classes?
going to be teaching. I'm teaching in astrophysics for majors.
Mhm.
So black holes, stars, galaxies, things like that. I'm the first astrophysicist they've ever hired. So
What?
that's exciting. Yeah, they have a physics department that has other kinds of physicists, but I'm the first astrophysicist.
So when they've taught astro classes before, it was non-astrophysicists having to teach that content? Gotcha.
Yes.
Yeah.
Yes.
So this will be fun because it's your area.
Right, exactly. And I'm also teaching a writing course about cosmology called The Birth of the Universe. And so it's getting people thinking about what kind of scientific ideas that we've had in the past that now are outdated, or talking about how our views on science change, how we can, just because scientists change their minds about something doesn't mean that you can't trust us and we don't know what we're talking about. It's that we look at evidence and we adapt to what new evidence will show us. And so the idea is to get people thinking about what ideas do we have now that we take for granted, or what ideas do we have now that in 50 years we'll think are totally dumb.
Mm-hmm.
And cosmology is a great place to do this because it talks about our place in the universe, and that has changed a lot over the history of humankind. So I'm excited.
So is it in the physics department?
No, they have required writing course that every incoming first year. So I get first year students. I get this opportunity, I'll call it, to really stamp their first semester in college. And so the orientation I went to today was talking a lot about you have to teach them how to be adults also, and how, life outside of the home for the first time maybe goes.
Have you ever taught college freshmen before?
I have, but it's been a while.
Yeah.
Yeah.
I had the opportunity when I was doing my master's, and then I started a PhD like 10 years ago and dropped out. But during the whole master's and then during the beginning of my PhD, I taught intro, like Psych 101, anatomy and physiology lab, and bio lab. And I have to admit that I loved my freshmen. I actually because I also, A&P lab, that was freshman too. I also taught animal phys lab, so that was seniors. And they were like they all had like senioritis and like didn't want to be there, and they'd just like do their
They're
work as fast
jaded
as they
already.
could and be like, can we leave? I have a date. You're like, okay. But the freshmen were so fun. And I also had the opportunity to teach in Texas. We had a program called TAMS, which is Texas Academy of Math and Science. So they were like really exceptional young students who started college at 16.
Okay.
And they had their own dorm. And so I often taught the TAMS classes. They would put them in the same sections because they were, not quite ready. I think they were intellectually ready, but maybe not emotionally ready. So I was teaching college freshmen who are also 16, who are basically children. And it was difficult for sure, but it was so much fun to like, I don't know, they would come to me after class and ask me questions, and I would be like, oh, you trust me.
I'm an authority figure.
But it's so weird, right? Like, do you remember that day when you realized that you're the professor and not the student? Like that day when you were like, oh, I'm closer in age. Like I could be these people's parents and they're not just like my friends anymore.
Yes.
Why does that happen?
I don't know. We get old.
I don't like it. So, okay, Oxy's new for you. So what were you doing before Oxy?
Before that, something very different. Before that, I worked. So NASA has a center on Caltech campus. Mm-hmm. And so I was a NASA employee, but a Caltech employee also. It's weird.
Wait, was it JPL or?
It's
gotcha.
Called IPAC.
I know IPAC. Okay.
And it's on Caltech campus, but you're sort of kind of Caltech, kind of NASA. Mm-hmm. And so what I did there was part research, my own independent research into galaxies. And then the other part was mission work. And so that can mean different things for different scientists. I was a staff scientist. And so my work there was, I was responsible for making videos using celebrities that communicated the sort of things that we're learning with NASA missions to the public. Because
oh my God, that's the coolest job ever.
It's so weird. I was negotiating with Hollywood agents, and this is what my PhD in astrophysics brought me to.
So were you working with like the Science and Entertainment Exchange ever? Did you partner with Rick at National Academies?
No.
Oh, interesting. Yeah, because it's so funny how in LA, there's actually a handful of these random kind of posts.
And we need to communicate better.
Well, SciComm, as we've known, because we both work in science communication and in academic science, it's still burgeoning. Like we're still kind of figuring out the ropes, and everybody's reinventing the wheel left and right. But we're starting to coalesce a little bit, I think.
Well, and particularly when you work for someplace like NASA, which is just so big, it was hard enough communicating within the different NASA centers and making sure we weren't reinventing the wheel, doing something that someone was already doing. And so, that was our piece of it. We made videos about the science because the NASA science belongs to everyone. Yeah. And so making it accessible is one step, but also making videos about it that people actually want to watch. Turns out if you put celebrities in them, that people will watch them.
I love it. So what were some of your favorite projects that you did?
So the latest project that we did, they just put out the second episode that I worked on while I was still there, called Universe Unplugged. And so they did the habitable zone. So it was sort of a take on the Twilight Zone.
Oh, fun.
And it's two actors from The Expanse and an actor from General Hospital. And they explore the universe, explore the galaxy, looking for habitable planets. Other planets where, and you explore what makes a planet habitable. What does that mean? If a planet is the right temperature, is that good enough? What else? The atmosphere, what are all the components that go into making a planet habitable for a species like us?
Oh, cool. And so I would assume then that also the point is that it had some of the latest science. And we used to think this, but now we know that, it may be a moon very far out could be habitable simply because of the tidal forces or, whatever. You're bringing new things into it.
Yes. And it was actually something that we had to work really hard at because we didn't use any specific systems. We didn't have them go to any known systems because that could be outdated tomorrow.
Yeah.
Our knowledge is changing so fast. I think the first exoplanet was found in the 1990s. And so
really? It's been that quick? 30 years?
And now we know thousands.
Wow.
And so we didn't want to put anything about a specific system and then have everyone be like, well, NASA is so outdated with their videos, right?
Yeah.
We want these to be long lasting. And so we just made example systems.
Oh, I love it. Okay, so you have been working in the Pasadena area for some time.
Yes.
And now Oxy, which is like right next door in Eagle Rock, my new hometown. And prior to that, I mean, is this your first position as a professor?
Yes.
How exciting. Is it something that you kind of knew you wanted to do? Were you like, God, no, I'm never going to stay in academia? Like, how did that kind of come about?
That's a really good question. I think that I didn't always know that I wanted to be in academia. I am among the first in my family to go to college, and I had no idea what that was about. And so it wasn't like something that I always saw as a potential career at all, even science. And what I think led me to being a professor is that I love doing science. I love doing research, and I was missing the student interaction as a staff scientist. So I get to do cool things like go make videos with celebrities. And maybe when I'm knee deep in grading papers, I'll regret my life choices for leaving that behind. But the connection of working with students and really making an individual difference that you can see right in front of you, I think that's what I was missing.
Yeah. I miss teaching so much. I think that it's something that once I finish my PhD, I'll always want to go back to. I'm not sure if I would be interested in a traditional academic position as a professor, like running a lab. I'm not sure, though. I am actually getting more. I don't know. I'm rekindling my love for research, but it had gone by the wayside for a little while. Are you going to have a lab at Oxy?
Well, so I was going to say, as an astronomer, you don't always need a lab. Some astronomers do, but for me, I go use billion-dollar telescopes either in space or whatever. And so I don't have one of those in my lab. But when I interviewed at Oxy, they showed me what would be my lab because it's a physics department. So I get like a lab like all the other physics professors. And I was like, what? I didn't know I wanted a lab, but now I want a lab now that I see this space. And it's just like a dark room in a basement, but I'm like, it's mine. I want it.
I love it so much. And is Oxy, I'm trying to remember, is it a graduate university or is it undergrad only?
No, they might have some graduates, but not. I think it's predominantly, well, it's definitely predominantly undergraduates.
I love that.
Yeah, they don't have any masters or PhDs in physics.
So you're going to have undergrad students that are doing like research credit or bachelor's level theses in your lab. Oh, how fun.
Yeah, and I just got a big grant from the National Science Foundation to support getting more students involved in the research. So I'm super pumped.
I love that. So, okay, let's talk about what that research is going to look like then. Because, when you were working for NASA as a staff scientist, you were doing things you were interested in, but they were projects that probably you were assigned to, right? Or did you get to actually create your own projects there?
For my own research time, I got to create my own projects.
Oh, you did? Okay, very cool. Yeah. And then you also worked on larger missions and things like that?
Gotcha. Which is most of your time.
Yeah. So your own research, your own interest area. What was your PhD actually in?
My PhD was in broadly galaxy evolution. So how do galaxies form and evolve? We live in a massive galaxy, the Milky Way, and trying to figure out, when you study galaxies, they evolve over incredibly long timescales. And so we can't really watch one evolve. Instead, we just get a bunch of snapshots of different galaxies. And so it's piecing together, what did this type of galaxy evolve into this one? Or are they completely separate evolutionary tracks? How do you get this kind of galaxy if it's particularly weird? And so trying to understand how we got here in this galaxy, how our galaxies formed.
Oh my gosh, I just had the weirdest parallel in my mind where like I study psychology and neuroscience, but I always grew up with a deep, deep passion for paleontology. I didn't end up pursuing it in academia, but I still am obsessed with it. I don't know, my books aren't organized, but at some point in time, you'll see that there's a massive dinosaur section.
Awesome.
And I know that there's a big part of paleontology. There's actually a really beautiful series at the Natural History Museum here in LA with Tyrannosaurus Rex growth series, where there's like a juvenile and then, or maybe it's actually like an infant, like a very young Tyrannosaurus Rex, a subadult, and then a full-grown adult. And for a long time, paleontologists didn't know if those were completely different species. They didn't know, because when you have so few examples and you can't physically watch them change, you have to kind of forensically piece this back. And I'm drawing this parallel with galaxy formation, that at any given time, you're just seeing them as they are. You don't know what they used to be like or where they're going. You have to kind of take information from the other bones or from the other evidence that you can find and start to sort of approximate the life cycle of a galaxy.
Yes.
So how do you do that?
Well, so one of the things that we can do in astronomy, you can't reach out and manipulate what you're studying usually. And so what you have to do, we tend to work, observers like myself who observe the sky and take data from that, have to work with theorists who simulate the formation of the universe. And we sort of act as checks on each other. So are the simulations predicting what I'm observing? If not, well, then we need to adjust them. And then what we're finding when we look out in the sky can help us figure out how we need to adjust and what tweaks we need to make. And so one of the things that I study in particular is, so we think that massive galaxies like the Milky Way that we sit in were formed from the merging together of smaller ones.
Okay.
A lot of things form in the universe like this. And so we think that you just get these little guys merging together and building. But this is a very complicated process because you don't add like one and one small galaxy together to get two, like a 2 times what you started with. You get something totally different. Like you add 1 and 1 and you get J, right? Like it's just because the act of slamming a galaxy into another one, as you can imagine, creates a whole bunch of cool physics.
Yeah.
Like you get intense star formation, you can grow black holes that way, things like that.
And so even like at the atomic level, there's like all sorts of weird stuff happening. There's like fusion happening and fission happening, and like you don't put in what you get out.
Right.
Or you don't get out what you put in.
And I studied for a while what happens when you slam 2 massive galaxies together, because massive galaxies like our own pack a big punch. They make really pretty images, and you can study them up close and also at a distance because they're very big, they're very bright, they're easier to see.
And do you mostly look at them with like where on the electromagnetic spectrum are you mostly studying these galaxies? Is it all types of astronomy or telescopes that you're using?
Yeah, I run the gamut pretty much. And that's because you learn about different pieces of the galaxy by looking at different wavelengths. So if you look at optical wavelengths, I use the Hubble Space Telescope, for example, you get to see stars.
So those are the pretty pictures we're used to seeing. Like if you have like a really beautiful wallpaper on your laptop, it's probably Hubble.
Probably Hubble.
Yeah.
Yes.
Gotcha.
Well, and partly because it has to do with the resolution that our detector technology, we can look at certain resolutions when in optical wavelengths versus, say, infrared wavelengths that are slightly longer. Infrared is showing you it can show you the dust in a galaxy. And so that's where stars are born out of. And so it gives you an idea of when you have a really dusty galaxy and they're bright in the infrared, something in there is heating it up. And so it could be star formation, it could be an active black hole. And so, but we can't quite get to the same resolution as we can with optical telescopes.
I see. And they look kind of murky too, right?
Yes.
Because of all the dust.
So they'll look, And then up to X-rays, which are super high energy. And so sometimes if you're trying to figure out, if you do have a dusty galaxy and you're trying to figure out what's heating it inside the dust, the optical light isn't getting out. It's like same if you had a dusty film on your window or something, you wouldn't be able to see through similar.
Yeah.
But if you shot an X-ray through it, then you could see that. And so X-rays make it out of this dust. And so, because they're very high energy.
Oh yeah, because they can see right through your skin.
Yes,
just straight to your bones.
Right,
Yeah.
right. So yeah, and then I also do radio wavelengths, which are very long wavelengths, and you can see the gas in a galaxy. And so one thing that does is when you smash two galaxies into each other, they the imprint in the gas is much more extended, and it can be left, it can last longer. And so you can sort of trace out better what happened. You can sort of put the rewind button on that galaxy merger using the gas a little bit better than you can the stars. And so it can show you what happened.
So, okay, this may be a silly question, but what comes up for me when I talk about all the different types of electromagnetic kind of what's the word I'm looking for? Detection. So telescopes that can measure X-rays, radio waves, visible light spectrum, all that good stuff. That's kind of like the type of astronomy that we've been doing for a very, very long time. It's it dominates astrophysics. And now, of course, we have gravitational wave astronomy, which is a totally different way of looking at the universe. So, but from what I gather, LIGO so far has been able to detect only things that are like several solar mass black holes colliding. So galaxies are obviously much, much bigger than that, right? And are we looking at black holes colliding through LIGO within our own galaxy, or are they like farther away from the Milky Way? Like, could you use gravitational wave physics to learn more about galaxies? Or are they too big and too far?
So for right now, the black hole mergers that we're looking at, so these are in the tens of solar masses. So astronomy uses solar masses as a unit. The mass of the sun is one solar mass. Yeah. And so because we're, egotistical, we compare everything to our sun because our sun is the best.
Isn't an astronomical unit the distance from the Earth to the sun?
Yes.
Too? Yeah, that's very egocentric.
Well, there's a lot of stuff in astronomy where like a dude named it this hundreds of years ago, never thinking that we would expand beyond this knowledge. And then it's like, oh crap, well, we've called it this forever. So
that's how you end up with like the English system of measurement where nothing is like divisible by 10 because we just arbitrarily set up anyway.
And someone was like, well, we're stuck with this because we don't like change. So actually one of the things that I'm trying to understand is when you have black holes, we have black holes that form out of the deaths of stars. So they're like stellar corpses. At the end of a star's life, it runs out of fuel, it collapses in on itself, and you get this incredibly dense object called a black hole. And so those are like stellar mass black holes. In the middle of galaxies, so what I'm talking about when you merge galaxies, there's things called supermassive black holes. Yeah. And that is the official astronomy term, supermassive. And we're talking billions of solar masses.
Yeah, because this is, when you think about like a sun, so our star is somewhat typical, I would assume, in the universe.
It's totally average.
Totally average. There are how many, like even in our own galaxy?
Estimate about 200 billion stars in our galaxy.
So when there's a black hole, like that's like a dying one of those 200 billion, or does it have to be bigger than our sun to be?
It has to be bigger than our sun, correct. Okay. But we estimate that there's about 1 million black holes in our galaxy. So that's
not counting the supermassive black hole in the middle of our galaxy.
That's not counting the supermassive black hole. So we have these like supermassive things, which are billions of solar masses. And then we have these stellar death remnant things that are, a few tens.
Yeah.
And then we don't, there's like a gap in between. And the crazy thing to me is that we don't know how supermassive black holes form. There's one in the center of our galaxy, there's one in the center of most galaxies, and they're pretty ubiquitous, but we don't know how they form. And so one of the things that I'm trying to do with my research is looking for black holes in the middle, intermediate mass black holes, because...
So like hundreds of solar masses or thousands of solar masses?
10,000 to 1 million, that range.
That's true. That would be the center point, right? See, this is the say, just to interject for a second, that always blows my mind when we have these conversations. And it reminds me too, I'm literally looking, right here on my bookshelf.
Yes.
You can hear me trying to move in this very heavy chair. I have my Powers of 10 flip book.
Yes.
You remember this? This old classic video.
Nice.
But it's one of those things where we so suck at scale.
Oh,
and so when we talk about the difference between a solar mass black hole or like 10 times a solar mass black hole, and those are the LEGO ones, like 10 to 20 times, versus a supermassive black hole. Oh, yeah, it's supermassive. It's like just way bigger. No, it's like so much bigger. It's almost unfathomable.
Yes.
Like we're talking, add how many zeros then to the end of that? Tens of billions. So that's what it did. 9? What?
Yes.
Yeah, nine zeros after that. That's a big change.
Yeah.
That's a lot.
Well, and the joke is in astronomy, order of magnitude is pretty good. Like if you guess, if you're off by 10, no, it's not too bad. Which, obviously in other things is, you hope your doctor's not off by an order of 10.
Don't build a house off by an order of 10. Yeah, you will die inside of it.
Yeah. So we're not sure how we get these supermassive black holes, but there's a couple of theories. One is that there were these special stars in the early universe that were first generation stars. So they're pure. They're born out of the Big Bang. And so they don't have any of these other elements.
Like nothing else has stuck to them yet.
Yeah, you haven't had a life cycle of stars to form the elements beyond what was formed in the Big Bang. And so maybe the seeds for these supermassive black holes formed out of those. Or the other theory is that you merge smaller black holes to get bigger ones, because that's how we make a lot of stuff in the universe.
Yeah, and stuff sticks to itself.
Right.
Because of gravity and all that good stuff.
Yes.
So just the same way that you make bigger galaxies, maybe that's how you made bigger black holes.
Yeah. Okay. So depending on how we can differentiate between these two theories, that's what I and many researchers try to do, right? How can I make observations that can help inform our theoretical predictions? And so one of the things that theory predicts versus when you're looking at these two competing theories is how many of these intermediate mass black holes do we find and how massive are they? Because if they're formed out of these first generation stars, we should see them all over the place, but they won't be that massive. And if they're forming from the merging of black holes, smaller black holes, then that's not going to happen everywhere. And so you're probably going to have a special situation. And so maybe you won't find them as frequently, but they'll be more massive when we do find them.
Where are we in our galaxy, by the way? I feel like when you see the T-shirts that say "You are here," and we're like out on one of the arms, like really far.
Yes.
Okay.
We're about halfway out.
Oh, we're halfway down an arm.
Yeah. If you drew a line from the center to the edge, we're about halfway out.
Oh, okay. So we're not as far out as I thought we were. Huh. I don't know why. I always thought we were towards the edge of the galaxy. Okay. And so our galaxy is kind of flat, right? It's a standard spiral galaxy.
Yes.
And you said we're just totally normal. Everything about us is just so normal. Like our sun is normal. Our planets are normal. Is the Milky Way normal?
Well, one thing about our planet system that so far seems unusual is that there's so many. We're starting to find more that have multiple planet systems, and so that's starting to be less true.
Oh, okay.
But when we originally started looking at finding exoplanets, planets around other stars, partly it was because of the way we were looking for them. We just weren't finding these systems that had lots and lots of planets.
And I mean, our ability to find them too, like the resolution at which we can find them is not great yet, right? So we can only see the really big planets.
It's getting better now that we're using different techniques. So we used to use a technique where, so we go around the sun.
Yeah.
Sort of. The sun and us actually orbit a shared center of mass, a shared point. But the sun is just so much more massive that it's just a teeny little wobble that we cause. Our pull on the sun is a teeny little wobble, whereas obviously we have this huge orbit around the sun.
Yeah.
And so we were detecting planets that way by looking for stars and looking for their wobble.
Oh.
And so, but that you preferentially find planets that are one, massive, and two, close to their star, because those are the things that are going to give you a bigger wobble. Now we can do techniques like the transit method.
How we found Venus, except from our perspective of our own sun. Right? Like when the transit of Venus, didn't we detect Venus because we saw it literally passing in front of our sun?
Maybe. I don't know.
I feel like that's how we knew Venus was there. But I just accidentally like deleted something in our file. That's okay. That's okay. No, I didn't delete anything. I just
Hopefully you deleted
it.
the part where I didn't know the answer.
No. Well, I know that we can watch the transit of Venus. This I know. We can literally put on like solar shades and we can look at the sun when Venus is set to transit. We can see the little bloop pass across and they're beautiful.
I just don't know the historical.
Yeah, I don't know if that's how we actually discovered it. We probably didn't. Probably someone was like, look, it's Venus because it's like you can kind of see it. It
is,
kind of big, right?
It's very bright in the sky.
Yeah, it's very bright.
Yeah.
Not as bright as Jupiter, but it's bright. I can always find Jupiter, so I feel like a good astronomer. Like that's because everyone can always find Jupiter.
It's funny when you get a PhD in astrophysics, they don't necessarily, you never take a class on like the constellations.
Yeah, isn't that funny? People think you do.
And people think I know stuff.
Well, because also the constellations are just like, it's just weird history. Like it's not really anything about anything except those kind of look like a picture that like some Greeks drew. Right? So how would you know?
And I've taught I do a lot of like visiting schools and things, and
fun.
I always want to tell the constellation stories to kids, but a lot of them are like, and then he got punished by being thrown into the sky, and like women don't fare very well in any of these stories. She was so vain, and it's like, okay, forget it.
Yeah, screw this. Let's just make up new ones that are all like super feminist and like really, like progressive. I like that.
And then she said, I don't care. I can do this myself.
And then nevertheless, she persisted.
Right.
That'd be so good. Yeah, that is funny. People think that you're right, that like astronomy is like stargazing. But it's, I mean, some of it is, and historically it was. But now you're stargazing with really cool tools.
Yes.
And it's not all stars. When I took astronomy for non-majors at my university, it was broken up into stellar astronomy and planetary astronomy. That's how they taught us. You could choose. So I took stellar astronomy, which actually was not as fun in lab because our lab involved going to an observatory. We actually had an observatory like north of our university. And I realized very quickly that looking at stars through a telescope, they still just look like stars.
Yes.
Every so often you can see two instead of one.
Right.
But that's pretty much the wow factor.
Yes. Yes.
Whereas the kids in planetary astronomy were like, oh, I saw like the banding in Saturn's rings. And I was like, no
so
way.
Cool. Yeah.
So we learned a little bit, but yeah, we didn't talk about what do you call them? Constellations either.
Yeah. Well, and when I grew up outside of a city, I grew up outside of New York City. And so there was no stars. And so for me, going observing for the first time was just seeing this, like how many stars there are was, well, life-changing sounds cheesy, but like I got addicted to that peacefulness and that quiet of observing and just seeing the vastness of even our little corner and understanding that there's so much more out there and also being able to control like billion-dollar equipment. I thought that was pretty awesome.
That's really cool. I mean, there's something so special, and I think I've gotten into it more and more as I've gotten older, and I've gotten more into like traveling the world and going camping and sleeping outside and things like that, of like really allowing yourself to stargaze in a true way, like only using red lights, like completely dark adapting, spending hours outside on your back, like lying down, setting up a really comfy spot on the ground with like sleeping bags and, bed rolls and pillows and lying on your back, listening to music. I think during meteor showers, sometimes it can be a really fun time to do it. But other times of the year too, like I'm always amazed and then I'm like not amazed. How many like quote unquote shooting stars you see because they constantly happen.
Yes.
You just don't know it because you're not dark adapted.
Right.
How often you can see satellites. You can always see satellites when you really start looking. How many stars you can really see and how even in places that aren't far from the city, like going to Joshua Tree, the Milky Way is bright in the sky, very bright. Like on a moonless night, it's stunning. Yes. And I remember the first time I saw the Milky Way, and I was like, "Holy wow!" Because I grew up in a city too. I grew up in Dallas, or the burbs right outside of Dallas, and you can see some stars, but just not really. Definitely not like New York, no. But no, like I think a lot of people have never seen the Milky Way.
Well, right. And to understand that it's a band across the sky when you're looking at it. And in the southern hemisphere, you can actually see our two closest galaxy neighbors, the Large and Small Magellanic Clouds.
Really?
So these are two, we call them dwarf galaxies. That's what we call small galaxies. And they are, I mean, you can see an entire other galaxy from the southern sky.
That's amazing. I think I saw with my scope, my little scope, which is upstairs. It's not that little, actually. It's like a 6-inch Schmidt-Cassegrain, and it's pretty powerful. If I'm really dark adapted with it, I can. It's a deep sky telescope, and I'm pretty sure that I was able to see. I mean, it wasn't really, really bright. I could faintly see with kind of that deferred vision thing, Andromeda pretty well through my telescope.
Nice.
Yeah.
Nice.
So it's doable. You might have to go to like Mount Wilson or something to do it. But we rented Mount Wilson once too, and it was so much fun. A bunch of our friends got together and rented the 60-inch there.
Oh, fantastic. I didn't know you could do that.
You didn't? Oh my God, you have to do it.
Okay.
It's like super expensive, but if you get enough people to do it, it's worth it. And you get it for, I think, 4 or 6 hours, and it comes with an operator and like a docent.
Okay.
And they will train it on something, and then everybody takes turns to see. Globular clusters at Mount Wilson are like mind-blowing.
Yeah.
Oh my God. It's so fun. Okay, now we're talking about stargazing, but you are a galaxy astronomer. And so is your active area of research now looking for those mid-range galaxies or those mid-range black holes? I went on so many tangents. What are you actively researching right now?
So I'm actively researching what happens when you smash 2 of these small dwarf galaxies together. So I had been studying massive galaxy mergers. Okay. So like what happens when like a Milky Way slams into a Milky Way or a Milky Way and Andromeda.
So a Milky Way and Andromeda are massive galaxies.
Yes.
Like we're
massive.
Average but large on the large.
Yes.
Yeah, okay.
We're like a typical large galaxy.
Gotcha.
And we think that they form out of the merging together of smaller ones, but we actually don't understand a lot about how those small galaxy mergers work.
Okay.
We don't understand because small galaxies, like massive galaxies like our Milky Way, have this really nice spiral structure. I
was wondering that. So we're mostly all spiraled like that because Andromeda is also spiraled.
Yes.
Okay.
And there are other ones called ellipticals that are more like balls.
But they're still roundish.
Yes. They have a clear structure, whereas these small galaxies are just a hot mess. They're all over the place. And it's partly because they don't have as much gravity to hold themselves together in an ordered fashion. And so you can imagine when you slam these 2 things together, what you get is even more all over the place than when you merge massive galaxies. And so
you mentioned the Magellanic Cloud. I'm Googling it because I want to see what it looks like. I wouldn't have even known I would call that a nebula.
Right. Well, and I mean, in earlier astronomy times, we didn't know the difference. We had everything was called a nebula until we figured out, wait a minute, these are actually a lot farther away than we think. Some of them were actually nebula and some of them were other galaxies.
Yeah, so this is not like dust and gas and crap within our own neighborhood. This is a whole other galaxy outside of the Milky Way. Right. But it's a baby galaxy. It's a dwarf galaxy.
Yes, it's a baby galaxy. And so a lot of questions pop out of studying these galaxy merging together dwarf galaxies. And so one of them is, can we find these intermediate mass black holes? Because we know in big galaxies, when you merge them together, you can inspire the growth of those supermassive black holes at the centers. And so if we have a dwarf galaxy, maybe it has an intermediate mass black hole since it can't host a supermassive black hole because it's not big enough. And so asking that question.
So we don't know that yet.
No, we don't. I think they're on the order of, well, it depends on who you believe, but there are, a couple to maybe on the order of dozens of known dwarf galaxies to host big black holes at their centers. Dwarf galaxies also don't really have centers either because they're just like messy blobs. And so I actually, my research was covered in the Wall Street Journal once, and they asked me for an image to go with it. And so I sent them like the best image that I had from, many hours on this gorgeous telescope down in Chile. And they were like, do you have anything better? It's like, no, that's what they look like.
Can you just like, do you have like a prettier one?
Yeah. They were like, what am I looking at? So yeah, they're just little fuzzy blobs, pretty much. But so lots of questions come out of this. One of the things that we looked for was, can we catch this process of these things merging together to form a massive galaxy in action? And so my group was the first to find groups of little dwarf galaxies hanging out without a massive galaxy in the middle. And so the idea is is this a snapshot of before they merged together to make that massive galaxy? And so we found some of those, which is really cool.
That's really cool. So they were kind of like, there was something about their positioning that made you think, based on, your scanning of the sky, that they were closely knit. Yeah. Right. So they're probably, or potentially probably like coalescing.
Yes. So we looked at, well, first they're close together on the sky, but then you can have projection issues where something appears to be close, but it's actually maybe way far distant, just really bright.
Or like really big, but far. Yes. Yeah, because that's our understanding of how big things are and how small things are have to do with how we see, right? Like it's like the cow thing. And I heard this thing in the UK where they teach kids distance. Somebody wrote in by having like small cows and big cows, because it's like, I don't know.
Because there's cows everywhere.
Yeah, someone was saying when they were kids, that's how they learned how large things are and how far things are.
Whatever works. Use what you know.
Exactly.
So we check for distance and from us to make sure they're also close. And then our next step is to use radio wavelengths to look for gas. And because the gas, if they're all sitting in the same gaseous envelope, that would suggest to us that they will eventually coalesce.
Oh, right. Because if they're kind of pulling towards each other anyway, there's going to be bits and pieces that are like sloughing off and moving faster.
Right. And the gas in a galaxy extends way beyond the stars. So even if the stars look close together, maybe they're just ships in the night passing by. That could still be true. But if they're connected via their gas, then they're intertwined. Their future is connected.
I love that. That's really cool. And so do we think that, for example, like the Milky Way, which is a typical large galaxy, is it young? Is it old? I mean, like, relative to what, I guess is the question. But like, are we a very mature galaxy? Or do we have like many more, things to learn on our journey?
Sure. Well, one of the ways you can sort of get an idea of how old a galaxy is, a proxy for age, is metallicity.
Okay.
And so metallicity is, I believe it's a word that astronomers made up, because whenever I type it into like Microsoft Word, it's like, this is not a word.
Yeah.
But there's a lot of things like that in astronomy. And also astronomers call metals anything that wasn't made in the Big Bang. So if it wasn't hydrogen or helium, it's a metal.
Okay, good to know.
Which most other people don't agree with. But in astronomy, that's a metal. And so in the Big Bang forms hydrogen, helium, trace amounts of lithium. And then everything else you have to get through stars. You have to get stars to process that hydrogen and helium to turn it into carbon, oxygen, everything else on the periodic table.
Yeah.
And so that takes time. And so you have, your early, a very young galaxy is going to be something that doesn't have a lot of these metals.
Gotcha.
Because it hasn't had time to process.
Yeah.
And then, or even turn its gas into a star to begin with. And so we sort of talk about how old a galaxy is based on how how much time it's had to process those metals.
So based on metallicity, and also I would assume based on how many like actual solid things there are in it. Like, are there stars? I guess stars are plasma, but like how many states of matter? Because like you said, it was mostly just, it'll just be gas before things start to, I don't know.
Yes. Yeah.
Like, what's the word I'm looking for?
Coalesce?
Yeah, I feel like I use that word too many times.
Right.
Yeah, but like before stars start to form, and then from that, things like planets and comets and, all the crap that's in a galaxy. It's like the actual physical kind of solid shit.
Right. Okay. So one of the things I looked at for my dissertation is, can we find galaxies that we've missed in optical surveys because they haven't formed a lot of stars yet. But
they wouldn't be bright.
Right. Yeah. But we searched in the radio, which will tell us if they have gas. And so we did find these faint fuzzy things that had plenty of gas. So they were still around the same size, mass as other galaxies. They just were late bloomers for whatever reason, and they hadn't turned that gas into stars yet.
So those could be young.
Yes, we would call those young.
Very cool. And so compared to them, is the Milky Way quite mature?
Yeah.
And what happens, like, we talk about like the heat death of Earth, for example, like when the sun finally burns out, our sun's probably not big enough to make a black hole, right?
No, it's not.
So it becomes
it's
brown dwarf?
White dwarf.
A white dwarf, okay.
Yes. So brown dwarf is like a failed planet.
Oh, gotcha.
Something that is a failed star. It's like bigger than a planet, smaller than a star.
Oh, like it never was able to become a quote unquote sun.
Right.
Like our sun is past the brown dwarf part. Okay.
Yes.
So then our sun became a sun, and it was like, rawr, I've got all the heat and all of the light, and I'm like sustaining everything in the.
And I'm going to do this for a really long time.
Really long time.
Yeah.
And then I'm going to start running out of fuel to react.
Right.
And eventually I'm going to fizzle out because I'm not big enough to implode.
Right.
Okay. So then it becomes a white dwarf.
Yes.
And then we all die because it's super cold.
Yes.
Yeah, which is bad.
It's going to be a major bummer.
Major bummer. And then, so that's happening all over the universe all the time, all happening within our own galaxy all the time. So what happens though? Like, how does a galaxy die, or do they even?
I don't know that they do. I mean, we haven't seen. Enough time has not passed in the universe since the universe's existence for us to see an entire galaxy go through something like that. Because remember, we have 200 billion stars in our Milky Way and 1 million black holes. So that's like less than 1% of these stars have already made it through the process to black hole. I mean, they could be white dwarfs and other things, but it's still a small fraction of the stars that have ended their lives.
Yeah, gotcha.
And it also depends on what the ultimate fate of the universe is in terms of, will we keep expanding and things get farther apart? Will we get a contraction where we all slam together in the end? It would, it depends on a lot of things that we just don't know. Yeah.
So kind of trying to test my memory, which is not good. Kind of a quick timescale review. The Earth is like 4.5 billion years old, right?
Yes.
Okay. The universe itself is not much older than that, right? Like Earth is really old compared to the universe.
The universe is about 13.8 billion years old.
And how old is, 13.8. Yeah, that's a number I remember. 13.8 for the whole universe, 4.5 for Earth. How old is the Milky Way? Milky Way age. 13.51. Yeah, it was that I was remembering. Like, our galaxy formed really soon after the Big Bang.
Right.
And like 300,000 years. That's it. No, 30 million years. I don't do the numbers. 13 billion. So that's 300 million years. About 300 million years.
Yeah. So, I mean,
that's a really long time, but it's not. That's the weird thing. It's not.
Right. Yeah. So, I mean, you don't have galaxies that are like babies today.
Yeah. Okay.
So when you ask me what's a young galaxy like, I'm talking about things that haven't evolved very much because they haven't turned their gas into stars, but that doesn't mean that they just appeared.
Right. Because everything
they've been
was
around.
Made.
Yes.
By the Big Bang.
Yes.
But also, here's another weird thing that's hard with scale. When we see things that are really far away, we're actually seeing them a really long time ago, right? Okay, this is crazy. So, like, how do we know when we look outside and we see, for example, a Magellanic Cloud? So that's outside of our galaxy. We now know this.
Right.
It's a little dwarf galaxy. It's outside of the Milky Way. So it's probably far away, right?
Yeah.
How long ago is it that we are seeing it now? Does that even make sense, that question?
Yeah. Okay. So if you look, that's why we talk about distances in light years.
Yeah, because it's like that time-space thing.
Right. Yes. That time-space thing always gets you. Well, so even the sun is 8 light minutes away. So if some, evil supervillain threw a blanket over the sun, we wouldn't know for 8 blissful minutes because that's how long it takes for the light to travel to us. And so galaxies, we start talking about light years away. The closest star to us is 4 light years away. No, is that true?
Wow. What's our closest star? Is it Vega?
Wait a second. I might have my units wrong.
That's okay. Let me look it up. Closest star. I love it. I Googled closest star and it autofilled to closest Starbucks. Okay.
Sad.
So the closest star, Alpha Centauri, A and B. Yeah. Why did I think it was Vega? I think because that's really bright.
No, Vega is the brightest one.
Yeah, it's the brightest, but not the closest.
Base all our magnitudes off that.
Gotcha. Okay. Yeah. So I know things.
Yes,
closest star, how far? It rhymes. Talk about 4.367 light years away.
Okay.
Yeah. So that's right.
Yes.
So that's far.
So the closest star is 4 light years away.
And that's our closest star, meaning it's like literally the closest neighbor we could have within our own galaxy.
Yes.
This is something we should have done at the top. And I feel like at this point, it's a little bit like rude to do now because like we're in deep. But like, just to be clear, like the sun, our planets surround the sun. That's the solar system. And then there's a bunch of solar systems potentially, or at least a bunch of stars. Yes. Solar system is also very like egocentric, right? Because it's like, it's our system. All systems are like our system because solar means sun.
I get corrected on that all the time because I call it a solar system, but
it's a star
it's a stellar system.
Yeah, stellar. Gotcha. Because that means star. Solar means sun, which is our star.
Right. So our sun is totally average in its mass and its color and everything, but also just being one of 200 billion stars in a galaxy, which is one of just 100 billion galaxies, right? It's
that we know of.
Right. And so the universe is really, really vast and really like this sounds like a ton of stuff, but it's also really, really empty.
Yeah.
The nearest neighbor is 4 light years away. And so we're talking about trying to send little people are talking about trying to send little light sails over there to visit our nearest neighbor. But like in all this vastness, humans have only made it to the moon.
Yeah, well, and our machines, right? Like one of the greatest accomplishments of humankind is that Voyager finally exited the solar system, the heliopause or whatever. Right. Like that's amazing, but that's just our own solar system is that big that we sent this shit off. Like Sagan was like doing these records in the 70s, right? And like it just like a year ago happened, or however long ago that was. So yeah, it takes time.
Yes, it takes a lot of time. Well, and I can't imagine working on a mission like that where you're going to send a probe to Saturn and you're going to dedicate your life's work to this, and then you're going to send it off into space, your baby, and then you have to wait a decade until it gets there and you see if everything worked out.
Yeah, and there's a chance that like it just died on the way. Yes. Like, oh God.
Unbelievable.
It's amazing. And I know I know plenty of people at JPL, you probably do too, who like are really interested in Jupiter and Saturn and some of the farther, like the what are they called?
Kuiper Belt objects.
Yes, Kuiper Belt. Thank you.
Asteroids. Yeah.
They're all very, very far away. Like Pluto. Dwarf planet now, right?
I know.
Yeah. So they still kept the word planet in there. I think they did that literally. Like they're like, yeah, fine. We'll call it a dwarf planet.
Right.
Because it's really just a Kuiper Belt object.
Yes.
Yeah. Just too emotional for us to be able to handle.
It doesn't clear its orbit. Yeah. That's the rule. You got to be able to knock stuff out of your way to be able to be called a planet.
Yeah. Yeah, because the thing that people didn't realize when that whole thing was happening, and they're like, no, we're losing Pluto. First of all, still there. Nothing has changed about it. It's a taxonomy issue.
Yeah.
But second, in order to keep Pluto means we're going to gain all sorts of other crap that is going to get very confusing.
Yeah.
So we don't want that.
Like basically if we found, it's one of these things where I was, we talked about astronomers tend to stick to conventions just because the way we classify stars by temperature, we started doing it alphabetical, but then it didn't work out because we found other ones and then we moved all around, or like the magnitude system where we picked a star that was the brightest star and we called that 0.
Yeah.
But then, whoops, we found some other things, right? And so now, like, 0 isn't, like, it's somewhere in the middle. And, it's a mess.
It's like when you are, like, going down the street in Santa Monica and there's all these little houses that, like, didn't used to be there. So they all have, like 42 3/4 is their address. And you're like, wait, what?
Yeah.
I'm just going to squeeze
Too many people live in Los Angeles.
So, okay, we've been talking about super interesting things, big things that are almost impossible to comprehend, but you do it for a living every day. One of the things that we haven't really touched on, I think we've sort of shimmied up against it just through how easy it is to talk to you on air, through the work that you're doing now in your new role at Oxy, the work you did in your position at IPAC, right? Is that you do a lot of SciComm, you do a lot of outreach.
Yes.
This is a big part of your life. And you actually work on your own podcast, right?
I do.
So tell me a little bit about Everyday Einstein.
So Everyday Einstein is a weekly science podcast that I do, and not just about astronomy. I'm not allowed to just write about astronomy. I write about other science. And so I'm not an expert in all science, but I am an expert in reading articles, and original articles and interpreting that information. And so that's what I try to do, from anything from things that are happening in the news and science that you're like, what are people talking about? To things like, is the 5-second rule a real thing? Turns out scientists actually researched whether the 5-second rule works,
Please
right?
Tell me it does.
It depends on the surface and how moist your thing is.
So you're saying is if you drop a lollipop into a toilet,
right, probably
5 seconds
just abandon the lollipop. Right.
But if you drop a lollipop onto a freshly mopped kitchen floor,
you're fine.
Okay.
You're fine.
Yeah. Gotcha. Especially if it's dry.
Yes.
You didn't drop it out of your mouth.
Right. That is preferred. Yes.
How fun to design those experiments.
Oh, yeah.
Do them.
Yeah. And and for me, it's really fun to write about that stuff because I get to pick what I write about and I get to think of questions that I've always had that I wanted to know the answer. And it's fun to sort of just get to expand out of my little niche of the universe every day. And it's a really short podcast. It's 5-6 minutes an episode. And so it's really just like, here's the highlights of what you might want to know about this. And I just feel very much that science should be accessible to everyone.
Yeah.
And science gets a bad rap for being too hard or for being, I think in science, if there's this sort of, I don't know, I love science communication because I feel like there's this pressure to sound smart as a scientist. Mm-hmm. And I've never felt that pressure.
Thank goodness.
I don't know why. But I mean, I remember as a grad student, me and this other grad student were interviewed for this discovery that we made in our research. And by a journalist. And he said all these things that sounded incredibly smart. But the journalist had no idea what he was talking about.
Yeah. So and then the journalist couldn't use it.
But then I would sit there and explain it. And then the ultimate article that came out would have all the explainer stuff for me, but then his really smart quote. And then, so he got these smart quotes and I was like, stars are cool, right? Like my quotes sounded really dumb, but I think that, it's useless. Everything that I do is useless if someone doesn't understand it. And we have these telescopes that are paid by taxpayer money. And so that science belongs to everyone. The sky belongs to all of us. And so I think we all have a right to that information. And so trying to make sure that it's presented in an accessible way, I think is super important.
Totally agree. So you mentioned when you were talking about preparing the episodes, you use the word writing, like when I write this, when I write that. So what's your process like for creating the podcast?
So I write something first and it has to get approved.
Because this topic is through an academic.
It's through Macmillan Publishing.
Yeah.
I can write about what I want. They don't check my content or pressure content or anything.
But because their stamp is on it, like they're the distributor and everything.
Yeah. I mean, they sometimes my editor will help me. She'll say, okay, break this down a little bit more. Sometimes she'll do that for me. But
she'll say, like, don't wait until the end of the episode to talk about the difference between a sun and a solar system and a galaxy. Yeah.
Right.
Thanks for that. It's a good note.
Right. But it's usually pretty minimal. And it's more and more minimal as I get better at it. Yeah. And usually my biggest problem is that when I write, I write very long sentences. And then when I try to say them, I'm like,
yeah, that's
because
really hard.
I haven't properly adjusted for
breathing.
Yes. And I you notice things like apparently I use the word however in my writing constantly, but that's not something I would often say, like however, like to a friend. And so trying to adjust for it's weird to write something and then say it. And so usually when I really get going, I stick pretty close to what I've written because I want it to be like a transcript for people who don't listen.
That's really great. That's something I can't offer as a service because it's so
way too long.
Yeah, it's so intensive. Like I wish I could afford to pay somebody to transcribe.
Right.
One of my listeners volunteered once, and then they were like, "Yeah, I'm never doing that."
No, it would take many more hours than to actually say it.
Yeah. And it is funny how much you realize that if you do screenwriting or you do just script writing, that writing the way that we talk as opposed to writing the way that we read literally, I don't know if that's a word, is totally different.
I get it.
And don't you get frustrated sometimes when journalists quote you and you say something really eloquently, but it doesn't really translate to the page right because they don't know where the punctuation is and they don't it's like, oh, it just sounded better verbally. I promise.
Right. And I never noticed this stuff before until I started, I'll make a list. It's really nice for our brains to read a list because you can tell clearly. But us talking, I would never say, well, first, and then second, and then third, because it's weird. And so trying to be true to the writing, but also be true to how I would say it if I were talking to you. It's something that I'm getting better at in the podcast. I actually, I realize how hard that is. And also interviewing people is really hard.
But it gets easier the longer you do it.
Yeah. I mean, you make it look very easy, but
I'm on year 5 or 6 of this podcast, and it's now when I do it in other aspects of my work, like I do interviews for psychology, to collect data, and I'm like, oh my gosh, it's so valuable all those years that I've been doing one-on-one interviews with people.
Yes.
Because it's a skill that you have to suck at until you get better at.
Yes.
But same as script, because, I do a lot of TV, which means I'm reading scripts all the time.
Okay.
And on-air work, requires that translation. And it's not uncommon when I'm in the VO booth reading copy that I'm having to kind of write it on the fly because it's not translating. It sounds too stiff. It doesn't sound like people talk. And the two biggest pieces of advice that I give myself that I learned from it is almost every time you write the word that, you don't need it. You can almost always get the word that out of there.
Yes.
And the other thing is contractions. Because people don't say it is. They say it's.
Yeah.
People don't say they are. They just say they're.
Yeah.
And that really makes things sound more conversational, right?
Yeah.
It's amazing how quickly those little changes can affect it.
Yeah. And I mean, I think in some of my earliest stuff, you can tell that I'm reading. And so I'm trying to get better at that.
My producers tell me all the time that it sounds like I'm reading my VO copy when I'm tired or, they're like, it sounds like you're reading. I want it to be more authentic. And the way that I always can flip out of that is to start talking with my hands a lot. So it's like they say actually the best way to do VO is to stand up, is not sit, but always stand and really use your hands when it's time to emote. I went to do that here and then over there and really, and it actually does translate into your voice. Yeah. It's so weird how you can hear a smile on somebody.
I was just going to say they tell you to smile. And I just had a baby. And so when you're pregnant, and when you're super uber short like I am, it has nowhere to go except into your lungs. And so it was really I listened to some of them and I'm like, so guys.
I'm sorry, the infant inside of me is kicking my lungs.
Pretty bad.
Oh my God.
So I had to stand to do that. But even then, it was hopeless.
Yeah, but you were uber pregnant too, so that must have been no, I just want to sit down.
Yeah.
So wait, how old is your little one now?
6 months. Yeah.
Oh, you're so sweet. So you've just now gone back to work. This is your first week.
Yes.
And now you're sitting here with me when you could be at home. That's it. We're closing out the podcast because I want you to get back to your baby. You know what? It's been a joy so far. I always close my episodes by asking my guests the same 2 questions. I love that we're doing this in person. So they're big picture questions.
Okay.
So get ready because they're good. Intense. I want to know from you in whatever context is relevant to you right now, especially considering everything that's going on. New job, new baby. Also, though, your work involves like the history and future of the freaking universe. So plenty to choose from here. In whatever context is relevant to you right now, number 1, what is the thing that kind of keeps you up the most at night? The thing that you really legitimately are like concerned about, maybe even a little cynical, a little like, ugh, not looking good. On the flip side of that, so we can leave happy. What is the thing that you're genuinely like truly excited for, optimistic about, looking forward to?
Okay. Well, my infant physically keeps me up at night.
Yeah.
So apologies for my brain. But I read that your brain is just as cognitively impaired with interrupted sleep as if you got no sleep at all. And I was like, well, great.
Yeah.
Don't tell my students. But no, I mean, for me, what is most concerning to me is definitely climate change. That does keep me up at night and thinking about what we have in store for us in terms of the things we know, but also the things we don't know. Like
the unknown unknowns.
Yes.
Yeah.
I mean, we've managed to make it 10,000 years with a very stable ecosystems have evolved. Our culture has evolved to be a certain way. And we just have this expectation that it won't change. And things haven't changed for several thousand years. And now we're changing things on a very rapid time scale. And so things like the little I was reading about, there's these little bark beetles that this change in temperature, suddenly conditions are more ideal for them. And now they're plowing through mid-latitude forests. And no one was worried about this bark beetle in particular. And now all of a sudden, well, sorry, maybe there's probably scientists that were actually worried about that.
Sorry, bark beetle scientists.
Sorry. But, it wasn't something that was, we talk about Arctic ice melting and things like that. I think there's a lot of things that we don't know what we're in for. And I mean, I have 2 children. I just had a baby. I have an older kid. And I think about what their future is going to be like. And I think they're going to look at me when they're older and say, when did you know? And what did you do about it? When did you know that this was a problem? And what did you do?
Yeah, and so how dare you? Because I couldn't do anything about it because I was not born yet. That kind of a thing.
Right. And so I'm getting chills. Like that.
And it's not even us, right? It's also our parents.
Yes.
Like that's the thing. We're the first generation to have to be reactionary, but we're not the first generation to have this information.
Right. And I am constantly asking my mom to stop buying her grandchildren plastic crap. And it's just, she thinks she worries about that environmental stuff, right? It's much
Isn't
more
that funny. It's just
part
culturally.
Of the, yes. Yeah. But on a happier note, I guess, one thing that does give me hope for us responding to climate change is that we've done it in the past. So like in the 80s, scientists noticed that there was this hole in the ozone layer.
Yeah.
And scientists did research and they found it was coming from these chlorofluorocarbons, the CFCs. And
like our hair's our Aquanet.
Right. And so we don't have Aquanet anymore, right?
Yeah.
We don't use them anymore. And people put pressure on politicians to ban them and we phase them out. And so now they're looking at the ozone layer and it's rebounding, and they think by like 2080, it'll be back to where it was before the 1950s.
That's amazing. So the fact is that the same non-mitigation strategies, the same just kind of like rampant use and abuse that can lead to these problems on an equal and opposite scale, mitigation strategies and like healthful decisions and forward thinking can be really curative and restorative and maybe even swing things in the other direction. But we have to agree that it's worth the money and the effort.
We have to actually do it.
Yeah, we have to actually do it.
Yeah.
And the part where it starts to feel hopeless sometimes is that we might agree, but other people disagree, or that there's political will isn't there, or there's political will in another direction because it's more financially, feasible. But it's getting to the point. I think the thing that gives me hope a little bit is that it's getting to the point where we can't freaking ignore it anymore.
Yeah.
Like
it's
even
really hot outside.
Yeah, like hardcore right wing, conspiracy theorists who are like, it's a hoax. Now they're saying like, okay, maybe it's not a hoax, but it's not our fault. Or okay, maybe it is our fault, but it's not financially feasible to do it. They keep moving the goalposts because they have to.
Right.
And that's actually a sign of progress, weirdly.
Yeah. We're getting somewhere.
Yeah.
Let's hope we speed it up a little bit. Yeah.
Yeah, exactly. But yeah, I mean, it's great that people who are innovative, who are really brilliant, who are, care about these things and are capable of solving these kinds of problems, are actively working on them with with laboratories and with funding and with, it's like we may not see it every day because we tend to publish only the bad news. Yeah. But there's a lot of good news too. Yeah. And we forget about that when we look at our iPhones first thing in the morning.
Well, because, the good news doesn't keep you up at night.
That's true. Bringing it back around. Well, Sabrina, this has been so much fun.
Yes.
Let everybody know now. Are you active on social media, or does your lab? Well, your lab's brand new, so it might not have a webpage yet. But how do people, find the podcast? How do they see what you're doing in your life, in your work? How do they keep up with you?
Sure. The podcast is Everyday Einstein, and I'm on iTunes, Stitcher, wherever you listen to your podcasts. So you can find me there. And I am on Twitter. I'm not super active.
But is that more like your kind of preferred social media outlet?
Yeah.
Me too. It's a science thing, I think.
I think it is too.
Yeah, we like Twitter.
Yeah. Yeah. At Doc Stierwalt. So my last name, which no one can spell correctly. So maybe it's a terrible Twitter handle.
No, it's good. At Doc Stierwalt.
Yeah.
See, that helps me because then I can pronounce it better too. Yeah. Sabrina Stierwalt, not Ciderwalt.
Right.
Sabrina, this was a blast. Thank you so much for doing this.
Thanks for having me. This was great.
Of course. And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.